All right, so let's have a little discussion on base equilibrium now that we know a little bit about acids. All right, to do that, let's remind ourselves of all the definitions that we have already established. So Arrhenius calls a base something that produces hydroxide ions in aqueous solution. Bronsted-Lowry says a base is a proton acceptor or H plus acceptor. And then the Lewis acid model says that bases are electron pair donors. So they have extra electron pairs that can be donated to an acid, basically. All right, so strong bases. Strong bases are basically going to be, at least for this class, going to be limited to the discussion of, whoops, went one too far there. All right, they're going to be limited to the discussion of group 1 and group 2 hydroxides. Okay, so we're talking about the first group or the second group of the periodic table. First group will always have the metal in that group plus the hydroxide, and they are very soluble in water, okay, so very strong. Group 2, so the second column of the periodic table, they are less soluble in water, so they're not always considered strong bases, but when they are, the pH of a strong base is going to be calculated directly from the concentration of the base in solution. All right, so here's a little chart that kind of summarizes it. So the first column is going to be sodium, potassium, lithium, rubidium, and cesium hydroxide. Okay, so here's all their formulas. All of these strong bases we'll talk about will have the conjugate acids H2O. And the Kb is very, very large. Okay, so these dissociate 100%. Now the group 2 hydroxides are down here, calcium, barium, and strontium. See that they have 2 hydroxides attached to them. Conjugate acid is still going to be H2O, but their Kb value is only large in dilute concentration. So we're talking about 0.01 molar or less. So for above 0.01 molar, they are not going to be considered strong bases, and we'll have to be given a Kb value for them. Okay? We will not assume 100% dissociation. All right, now weak bases, basically, they are going to react with water to produce the conjugate acid and the hydroxide ion. Okay, so here is a weak base reacting with water. It gains the proton and then from water, and then you have a hydroxide ion left over. Notice the Kb value is much smaller than what we were dealing with before. When you write the Kb expression, it is products over reactants, and H2O doesn't have to go in because it's a liquid. Now here are some common weak bases. A lot of people have a hard time with identifying weak bases and their conjugate acids, okay? Here's something that should help you. If you notice, all of the weak bases given here have nitrogen and hydrogen associated with them, because that's a big hint there. Oops. And here, you see that every single one of them has a plus sign when they have the conjugate acid, so they gain that H plus, okay? All have small Kb values, so -3 to -10, so all really small. So when we're talking about Kb, that is the equilibrium constant for the reaction of a base with water, and it's given, its equation is going to be the conjugate acid of that base, which is going to be BH plus, and then the hydroxide ion over the base itself. Okay? All weak bases do this. Do not complicate it and try to make it something that it's not. They all do this. All right, so here's a weak base equilibrium problem, and let's see if we can determine some steps to help us solve.
All right, so the first thing we're going to need to do is write the actual equation for the reaction. So we have NH3, and you throw it in some water. So NH3 is ammonia, throw it in some water. NH3 is a base, so it's going to gain a proton, so NH4 plus, and then we're going to have hydroxide ion left over from the water. So we're going to need to ice this because it's not all going to dissociate because it's weak. And then we're going to write our equilibrium expression, solve for x, and then we're going to have to convert. All right, so we started with 0.5 ammonia, okay? So we don't need H2O because H2O is a liquid, so it doesn't count. So ammonia is in this one, and then you've got NH4, and then you've got OH minus. So we started with 0.5, 0, and 0. So we're going to have minus X, plus X, plus X. So we have 0.5 minus X, and then here we have X and X. Okay, so now we need to write our actual expression. So we have K equals NH4 plus, okay, and OH minus. All right, and that's all over NH3. Remember, water doesn't count because it's a liquid, and the concentrations of pure liquids and solids are always 1, so we don't have to deal with them. All right, now we're just plug it in. So the top is x squared, and then the bottom is 0.5 minus x. Now that's equal to our K value, which was, let's see, 1.8 times 10 to the negative fifth. Okay, so there's our K value. K is small, so anything that's added or subtracted from a normal number can be ignored, so I can cross that out. So I have 0.5 times 1.8 times 10 to the negative fifth to get that 0.5 off the bottom. Gives us 9 times 10 to the negative 6. And that's equal to x squared. Now square root it, and we get 0.003, or 3 times 10 to the negative third. Okay, so that's our x value. All right, now x, remember, is the value of the OH concentration. So now that we know OH concentration, so this is OH concentration. All right, so now I can do the POH equals the negative log of the OH concentration. Sorry guys, I'm really not sure why my pen's making all these swirlies. I'm not intending on doing that. All right, so POH is, so negative log of 0.003, so POH is equal to 2.52. And that means that pH plus POH equal to 14. So here's our POH. So 14 minus 2.52 will give us our pH, and I get 11.48. Because that's our pH of the 0.5 molar solution. Okay, so let's look at one more problem. All right, in this one we have a strong base, and we know that that's going to dissociate completely because it's NaOH. 0.5 molar, so we can basically assume the concentration of the base is the concentration of the OH. So 0.5 is our OH concentration. So we can do POH is equal to, good Lord, look at my pen, is equal to the negative log, must have it on some kind of funky curling pen thing. I'll have to fix that. So negative log of 0.5. And that gives us a POH of 0.3. Now pH plus POH is equal to 14. So 14 minus 0.3 gives us our pH, which is 13.7. Okay, so no ice table needed there. And there's our pH.